Let's start with our first system property, and that's linearity. So we'd like to be able to tell if a system is linear or nonlinear. So a system is linear, and a continuous time system is linear, if when we apply h, remember h is our notation for a system, if we apply it to a linear combination of input signals, we get the same linear combination of the output signals. So that is h of x1 of t and h of x2 of t are the output of the system with input x1 or input x2, and we just get the linear combination of the output when we apply h to the linear combination of the input. And we see the exact same thing for discrete time. Same formula, h of a1 x1 of n plus a2 x2 of n is a1 times h of x1 of n plus a2 times h of x2 of n. Right, so this is just this linear combination property. It's helpful to see this in a different way, maybe through some pictures. So here it is in pictures. We start out with a1 x1 of n plus a2 x2 of n. That's happening at the output right here. Then we pass it through h, and we're saying it's the same thing as if we applied h to each of the signals, then applied the gains, and then did the addition. Right, so in some sense we can think of what's happening here is that h is getting pushed through the adder, and then we make copies of h, and then they move before the gains. Right, so this is a manipulation of a block diagram and shows some of the power of this block diagram thinking when thinking about systems. This linear combination doesn't just have to be for 2. You can use that property for 2 to show that for any finite sum, so if I have a sum of n, capital N terms, so ak, xk of n, sum of all of those, if I apply h to that, then I get the sum of the ak's and then h applied to each of the systems. So this h, again, I can push it through, I can sort of push it through the system here, and then I'll get the following. See, I've pushed it through the summation and then pushed it past the gains. So in some sense, the gains and the h, we can think of those as commuting. This trick even works for infinite sums. So again, I can take an infinite sum of x1 of n, x2 of n, xk of n, all the way, going from k equals minus infinity to infinity. And then I can apply h, I can apply the gains, and then I can sum them and apply the h. And again, I can push the h through, and it said apply h to each of these individual signals, x1, x2 to xk. I can apply h to those, and then apply the gains, and then do the summation. So here we have it. So those two systems are equivalent, and that's what linearity buys you. So when you have a system is linear, you can do this swapping around, pushing through summations, and so on. So how do we check if a system is linear? So the basic thing to do is to check the definition. So let's look at a first example. Suppose we have a system that is a modulator. It takes x of t and multiplies it by cosine 600 pi t. So the 600 pi is the omega c that we saw before when we looked at modulators more abstractly. So let's check out linearity. Well, if I apply h to a linear combination of two signals, then I get a1 x1 of t times plus a2 x2 of t times this cosine. And then if I just multiply through, I can see it indeed. It is a1 times x1 of t cosine 600 pi t, 6000 pi t, plus a2 x2 of t cosine 6000 pi t. So that is actually just a1 times h applied to x1 plus a2 times h applied to x2. So this system is, in fact, linear. What about if I put the x of t inside the cosine? So I do 6000 pi x of t. Then if we try to apply h to this, we plug in the linear combination, cosine 6000 pi times a1 x1 of t plus a2 x2 of t. Looks like I have an extra parentheses here. This is not equal to a1 times cosine, because the cosine of the sum of two signals is not the sum of the cosines of those two signals. We know that from trigonometry. So the important thing to note is that in order to prove that a system is linear, it has to be linear for all possible input signals x1 and x2. So if you suspect that a system is not linear, then what you need to do is cook up an example and try it out, like this 6000 pi x of t is the system, we can try to cook up a simple example. Either you can prove it directly, or you can find just one for one x of t, or one x pair x1, x2 of t, that this whole thing will fail, and then that will prove that it's not linear. So try it out yourself. You want to determine if each of these systems is linear or nonlinear. The instantaneous power, the downsampler, the this x of t minus 2 plus x of 2 minus t, the derivative system, and the system which outputs the even part of the signal. So try each of these and see if you can show whether they're linear or nonlinear. And that'll help you get a feel for how this property works and how to tell, kind of get a good guess, given a new system, whether it's linear or nonlinear.